This is a revision video for the second organic chemistry topic in AQA A-level Chemistry. It's an opportunity to ensure that you've learned the key facts from the specification without including any of the applied procedural questions. The questions are available as a worksheet in the description below, so download them, answer them, and then use this video to check your answers. An alkane is a saturated hydrocarbon and it has the general formula CnH2n plus 2. So in other words, if I want to know the formula of an alkane with 8 carbon atoms, it'll be C8H and then 2 lots of 8 is 16 plus 2 is 18. The first 8 unbranched alkanes are methane, ethane, propane, butane, pentane, hexane, heptane and octane. In physical chemistry, you've learned about 3 different kinds of weak intermolecular force, and between alkane molecules, the ones that we find are van der Waals forces. As the molecules get larger, there are more electrons to play with, and therefore these van der Waals forces get stronger. In this instance, we don't have to worry about any changes in polarity. We're comparing 2 very similar molecules, they're both hydrocarbons, just one is bigger than the other. As these forces become stronger, this means that more energy is needed to overcome them, and therefore the boiling point increases. Fractional distillation separates mixtures of fluids according to their boiling point by heating and cooling them. So in order to undertake fractional distillation of crude oil, firstly the mixture is heated, and while there isn't a specific temperature that you need to know, this is going to be somewhere in the region of 400 degrees C, maybe 350, somewhere around there. Because they've been heated up to such a high temperature, the vast majority of the hydrocarbons evaporate, although there may also be some residue left behind like bitumen. Once the hydrocarbons have evaporated, this mixture of gases are pumped into the fractionating column, and this column has a temperature gradient. In other words, it's not the same temperature everywhere. It's hottest at the bottom because this is nearest to the heat source, and then as we get further away from the heat source, it cools down. The molecules rise, and then as they reach the temperature that corresponds to their boiling point, they condense and turn back into liquids, allowing them to be collected. The largest molecules are the ones that have the highest boiling point. And this means that they turn back into liquids first, and so they condense lower down the column and they can be collected at lower heights. This means that the differences in boiling point lead to physical separation of the different fractions. And remember that a fraction is a group of molecules that have similar properties, they're usually similar chain lengths, and they'll have similar boiling points. Vacuum distillation is particularly useful when we're trying to separate out the very high molecular weight alkanes. Sometimes in fractional distillation, these are sort of left behind at the end as one residue that contains a lot of very large molecules that haven't been properly separated out. Part of the reason for this is that they have very, very high boiling points. So in order to separate them further, a really high temperature would need to be used to make some of them turn into gases. Because we're using a vacuum, there is low pressure, and at low pressure, the boiling point of these molecules is lower. So this means that a lower temperature can be used, and therefore it's more energy efficient. In industrial fractional distillation, the different fractions of hydrocarbons are separated spatially or geographically. In other words, they're condensing in different places. But when we do fractional distillation in a chemistry lab, in a school, then the different fractions are all coming out of the same hole, the same piece of equipment, but they're coming out at different times. In other words, they're temporally separated. So in order to separate the hydrocarbons, firstly we need to heat a flask, and this is often done with a heating mantle rather than a Bunsen burner because we're trying to avoid igniting the very volatile fractions. And to start with, the temperature isn't particularly high. To begin with, we may be looking at 40 degrees or 50 degrees, so it's just the smallest hydrocarbons that vaporise. But gradually, as the temperature rises, larger and larger hydrocarbons vaporise. Also, in order to get the hydrocarbons to turn back into a liquid, we can't just rely on them getting farther away from the heat source, so instead we use a condenser. The 2 types of cracking that you need to know about are thermal cracking and catalytic cracking. As the name suggests, thermal cracking takes place at a very high temperature, and while there isn't a specific temperature named in the specification, this is in the region of 900 to 1000 degrees C. Also, unlike at GCSE, where we weren't allowed to mention pressure, we can now say that it happens at very high pressure, something in the region of 70 atmospheric pressures, so that's 7,000 kilopascals. And thermal cracking, when you do it, produces a lot of alkenes and then smaller numbers of alkanes. In contrast to this, catalytic cracking can happen at a lower temperature. We're not talking low, we're not talking room temperature, but something in the region of 450 degrees C. And it can happen at low pressure, barely more than atmospheric. As the name suggests, it requires a catalyst, and the specific catalyst we're thinking about is a zeolite catalyst, which is an aluminium silicate. Rather than producing lots of alkenes, catalytic cracking produces lots of branched hydrocarbons and also aromatic hydrocarbons, in other words, ones that contain benzene rings. Hydrocarbons are cracked because there's a much higher demand for the shorter chain hydrocarbons, and they're sort of in short supply. And the reason for this is that they are much more flammable and therefore they make much better fuels. Combustion is the oxidation of fuel to release energy, and it can be split into complete and incomplete combustion. Complete combustion happens when there is sufficient oxygen for all of the carbon in a hydrocarbon to be fully oxidised, and it produces carbon dioxide and water. Incomplete combustion happens when there's insufficient oxygen for this to happen, and it can produce slightly different products depending on how little oxygen there actually is. So it may produce carbon monoxide and water, or possibly just carbon particulates and water, but usually we're thinking about some kind of mixture of these and probably some carbon dioxide in there as well. You should be aware that carbon dioxide, methane and water vapour are all examples of greenhouse gases. Short wavelength radiation is able to penetrate these greenhouse gases and reach the Earth's surface. When it does so, it's absorbed by the Earth, and then this is re-emitted as waves that have a longer wavelength. So for instance, infrared radiation rather than visible light. The bonds in the greenhouse gases respond to this radiation by absorbing it and then vibrating. And this means that that radiation doesn't actually escape through the greenhouse layer and back out of the atmosphere into space. And so overall, the Earth's temperature warms up. Various different oxides of nitrogen can form in a combustion engine when the oxygen and the nitrogen from the air react with one another, but this can only happen at very, very high temperatures, which is why it doesn't happen just normally out in the world apart from when there's a lightning strike. A catalytic converter can work when 2 molecules of carbon monoxide and 2 molecules of nitrogen monoxide react together to form 2 molecules of carbon dioxide and some nitrogen. Whereas a homogeneous catalyst is in the same phase as the reactants, for instance when you have an aqueous catalyst and an aqueous set of reactants, a heterogeneous catalyst is in a different phase, so for instance a solid catalyst compared to gaseous reactants. A typical catalytic converter that you find in a car or a lorry has a honeycomb ceramic support, so in other words it has a big cylindrical block that has lots and lots of little holes in it. And this is covered in a wash coat that contains platinum group metals, so that could be platinum, palladium or rhodium. Because it has this honeycomb structure, it has a very, very high surface area, and this means that really small amounts of the platinum group metals can be used, and this is important because they're very, very expensive. Crude oil often contains sulfur impurities, and so when a fuel is being burned, alongside the hydrocarbons being combusted, that sulfur is also able to react with oxygen to produce sulfur dioxide. This is problematic because when sulfur dioxide dissolves in water, it produces an acid called sulfurous acid, and this causes acid rain. In order to get around this, when you have power stations that are burning large quantities of these fossil fuels, the waste gases are reacted with either calcium carbonate or with calcium oxide, and this is going to produce calcium sulfite and carbon dioxide, or if we just react it with calcium oxide rather than calcium carbonate, then we produce the same salt but without the carbon dioxide. Thank you very much for watching, and I hope you found this video useful for your revision. If you did find it useful, then don't forget to let me know in the comments below, and don't forget to like and subscribe for more A-level chemistry content coming soon.